Hi everyone, and welcome to the ICP Zero to Dapp Educate series powered by Encode Club. This is the first out of 8 sessions of our educational series, which will take place each Tuesday and Thursday at 5:30 GMT. Please write in the chat where you're from, GM, where you're based. I'd love to hear where everyone is. Today, we are going to hear from Moritz, who will be joining the stage very soon. Hi, how are you?
Hello, everyone. Doing great.
Good, good. Are you excited for the first session?
Yes, very excited.
Great. So if you have any questions, feel free to pop them in the chat. I will try and kind of answer them throughout. You can also DM me on Discord if you have any questions. I've written my handle in the chat. And if you don't have access to the Discord channel for this series, then let me know and I'll try and help you out. But other than that, I'm just gonna hand over to Moritz for now, and enjoy, everyone.
Thanks. Yeah, although you already learned a bit about me, I'm still going to give you one more quick intro about myself. So my name is Moritz. I've been active in the DFINITY community for more than 5 years now. I've been building dApps on the IC since mainnet launch in May 2021. And I've joined DFINITY as a developer relations engineer about a year ago. And as part of that role, I'm handling grants, I'm creating educational material, I'm trying to improve the developer experience, and I'm one of the go-to persons for developers in our ecosystem if they have problems or they just want to have like someone to discuss an architecture or something like that. And today's presentation is going to be a high-level overview of the internet computer. And for the sake of time, I won't be able to explain everything in detail because there's really a lot to unpack. But if there's anything or something that you'd like to know more about, keep an eye open for QR codes in the top right corner of my slides. But you don't have to keep your phone out all the time trying to scan them because this presentation is actually public. So I will share the QR code at the end, so you don't have to constantly try to catch them. And before we start, I want to encourage everyone to join one of our communities. Having a community is great for networking, for sharing knowledge, getting help, staying updated, and also to get motivation and support from your peers. So if you build something, it's really nice to have a community. And the first community I want to mention here is our community-led developer Discord. That's a great place if you want to ask smaller questions where you expect the answer to be rather quick. And it's also a nice place to hang out with like other developers building an ecosystem. Also, if you, for example, participate in a hackathon, it's a nice place to maybe find someone to participate in your project. The second community is the developer forum. This is a place you go to when you really want to go into depth with a question or a discussion. And it's also the place where DFINITY, for example, shares roadmap items or where anticipated new features are discussed with the broader community. And the last one are ICP hubs. Those are spread across the globe, and they are basically local, on-the-ground communities that organize also hackathons, meetups, events. So yeah, if you follow that link, you will see a map that outlines where those hubs are located, and maybe there's someone that runs a hub close by where you live, where you can join IRL. Let's also quickly talk about who I'm working for, which is DFINITY, a Zurich-based not-for-profit organization that has been founded in 2016. We have more than 270 employees that combined have more than 1,600 publications and more than 100,000 citations. DFINITY is probably the largest R&D team in blockchain with more than 250 employee patents. And of course, DFINITY is a major contributor to the Internet Computer Protocol. So with that out of the way, let's start our little journey here with the following question. What's the vision of the internet computer? And to understand that vision, we have to take a look back to the days of the early internet pioneers. Those guys imagined the World Wide Web as a great equalizer. So in their mind, the internet was supposed to be a place to foster freedom and to have information and data easily discoverable and shareable. And the internet computer extends this vision with computing capabilities on top of a blockchain. So the internet computer does to computation what the internet does to communication. And before going deeper into DIC, let's take a look at the history of blockchains at a high level. So first, there was Bitcoin, the first blockchain to create a public ledger without a single point of trust. Bitcoin relies on proof of work, so it's not really efficient, but it still acts as the crypto world's store of value. And of course, Bitcoin basically started this entire revolution by showing that decentralized systems can actually work. Then came Ethereum, which again changed the world. Technically, Ethereum is an evolution of Bitcoin, so Ethereum extends Bitcoin with smart contracts, and therefore it created the world's first smart contract platform. So it's not just a ledger, but you can actually run arbitrary code on Ethereum. But Ethereum still has its limitations. For example, it's not really scalable and also not that performant. And then the internet computer, a third generation blockchain. The internet computer does not rely on proof of work, and it's built on a foundationally different distributed system. And the internet computer solves problems that Ethereum has not solved with its evolutionary step. And this means that the internet computer is a horizontally scalable blockchain that's able to run very general smart contracts or even host web pages and enterprise software. So the internet computer makes it possible to run any application and computation on top of a blockchain and realizes the vision of a globally decentralized, unownable digital computer. So now let's take a closer look at the internet computer's architecture. The internet computer is designed to be decentralized at the infrastructure level already. So at the bottom of this infrastructure, there are independent data centers that are distributed across the globe. So a data center is a place that's designed specifically to host computing systems, like, for example, servers and data storage arrays. An independent data center here means that there's no cloud involved or no cloud providers involved. So none of those data centers are owned by AWS, Microsoft, Google Cloud, or anything like that. And this means that the internet computer actually forms a sovereign network, while most other blockchains basically just run in the cloud. Ethereum, for example, has 53% of its nodes running on cloud infrastructure. So within those data centers, we have nodes that are being run by node providers. A node is a single physical machine and runs a special software to participate in the internet computer protocol. So the internet computer protocol creates the internet computer blockchain, and it ensures that the nodes agree on the sequence of computations that have been carried out. Those nodes, again, form subnets. So a subnet is basically an independent blockchain, and every node can only be part of one subnet. So the internet computer doesn't consist of one subnet, but it consists of many subnets that are all being run in parallel. So a subnet is a replicated state machine, and that means that each node within the subnet performs the same computation on the same state. And which node is part of which subnet is decided by a DAO, the Network Nervous System, which is an on-chain governance system on the internet computer. And the decision is always made to maximize decentralization. And that is that each subnet should consist of nodes from as many independent node providers, from as many geographically distributed data centers as possible. And we call this deterministic decentralization. So we already learned a bit about ETH, where a majority of the nodes basically run on cloud. But for Bitcoin, the situation is actually similar. I mean, this number is old, but in 2019, roughly 70% of all the Bitcoin miners actually came from China. So the point I'm trying to make is that it's not really like the amount of nodes that are being run that is important, or like that's an important metric, but it's more important who's running them and where are they run. So even though a subnet might not have hundreds of thousands of nodes, it might still be more decentralized than a blockchain of that caliber. And something very special about subnets is that they can seamlessly communicate. And that in turn means that smart contracts can seamlessly communicate with other smart contracts in different subnets. And this feature allows the internet computer to scale horizontally. So if the internet computer needs more computation or storage, it will just add new nodes and form a new subnet. And one important technology to connect subnets is chain key crypto. So chain key crypto uses a threshold signature scheme. And this means that the secret key is split up into secret shares, and each share is stored on a different node in a subnet. So to sign a message, nodes must coordinate to generate a signature in a distributed fashion. And it's very important to note here that the private key is never reconstructed in one location. So even when the subnet is signing something, the private key is not like reconstructed or available to someone at some point in time. And this allows every subnet to hold a single distinct public key. On this slide, this is denoted by this old looking key that's hovering above the subnet. And the public key can be used to verify outputs of the internet computer by simply creating a signature on them. And this includes responses to ingress messages from users and also messages between smart contracts. So on the internet computer, you only need to know a single public key and verify a single signature to be able to validate a response. And this is a key technology to enable the unprecedented scalability of the IC, as a subnet only needs to be aware of other subnets' public keys to trust a message coming from them. So to put this into perspective, on other chains, you need to run the protocol basically from the Genesis block to be able to validate the current state. So for Ethereum, for example, you would need to download hundreds of gigabytes. On the internet computer, a single 48-byte public key is enough to achieve the same. And there are a couple of other use cases for chain key crypto. For example, it's also used to verify the entire state of a subnet at regular intervals. And this enables a number of functions, such as adding new nodes to a subnet and allowing, for example, a crash node to quickly catch up to the rest of the nodes. And it enhances both the scalability of the IC, and it's also crucial to enable the topology of the IC to autonomously evolve over time. It's also used as a way to create a source of unpredictable pseudo-random numbers, and those are actually made available to smart contracts on the IC. So on the IC, canisters or smart contracts have access to randomness. And this mechanism, or this randomness, is also used in the mechanism that selects the leader in the internet computer's consensus protocol. So as you can see, chain key is really a fundamental part of the technology stack of the internet computer. So now that we know how the internet computer operates and scales, let's talk about canister smart contracts. So canisters combine code and state in one place. So each canister that you upload to the internet computer is assigned to one subnet. And as we already learned, canisters are able to communicate with each other, and that not only within a subnet, but actually across the boundaries of subnets. So when you are deploying your canister on a subnet, you have to compile your code from a high-level programming language into a WASM module. And WASM, or WebAssembly, is a low-level computer instruction format that's portable and abstracts program execution cleanly over the most modern computer hardware. And in theory, all languages that compile to WASM or that have an interpreter that can be compiled to WASM can be used to write canister smart contracts for the internet computer. And canisters are probably, from the concept that you have in your mind right now, an evolution of smart contracts. So I think it's easy to think of them as a decentralized server. So let's go over some of the unique benefits and features that canisters offer. So the first one is that as a developer, you can easily and securely authenticate your users with internet identity. And we will mention internet identity a bit later, and there's also going to be a session on internet identity in this education series. Also, thanks to the reverse gas model, your users don't need to know anything about crypto, wallets, or tokens. Reverse gas model means that canisters on the internet computer, so smart contracts on the internet computer, are pre-charged with gas to pay for computation. You can also call into Web2 services, like, for example, an exchange rate API, to fetch the current token price and forward it to your canister smart contract. It's also very, very strong because it kind of replaces oracles. Also, canisters operate at web speed. And that means that your users don't have to wait for ages for a transaction to finalize. So currently, transactions on the internet computer have a 2-second finality. And what this means is that canisters can offer your users almost the same experience that they are used to from Web2 in general. You can also basically build anything within a canister. For example, games, DeFi applications, large-scale social media applications, even AI models running in a canister, or enterprise solutions. Also, canisters can serve APIs over HTTP. And this makes it extremely easy for traditional developers and applications to integrate with them. Another big topic is storage, right? So canisters can store huge amounts of data. Currently, you can store almost 100 gigabytes of data within a canister, with plans to enable terabytes in the future. And last but not least, another very important feature, canisters can natively serve websites, allowing you to deploy your Dapp's tech stack 100% on chain, so there's literally no cloud involved. So let's compare the user experience between generation 2 blockchains, or the Dapps built on top of generation 2 blockchains, and the user experience of Dapps built on the internet computer. Let's talk about Ethereum, for example, because it's the most prominent one. So if a user visits a Dapp, they first get a website that is served from AWS or another cloud provider shipped to their browser. Then they are probably pretty quickly prompted to install a wallet, which is usually a browser extension, before they can use the Dapp, really. The next thing they have to do is that they have to set up the wallet, right? They have to secure their seed phrase, maybe understand how it works and stuff like that. So now they think, I have a wallet, I have the website, I'm ready to go. But when they want to interact with the Dapp, they realize that they need Ethereum to pay for the gas fees. So now they have to sign up to an exchange, they have to do KYC, they have to connect their bank account, they have to purchase ETH, they have to send the ETH from the exchange to their wallet and then come back to the Dapp. And then they use the wallet to interact with a smart contract on Ethereum through a centralized RPC provider, with each interaction taking a long time to finalize. And by doing all of that, users also have to trust that the cloud where the website has been served from isn't hacked or malicious, and that the RPC provider doesn't behave maliciously. So I would say that that's a pretty bad user experience, and that this model is nothing that will allow us to onboard the masses onto crypto. On the internet computer, on the other hand, canisters can serve content for browsers and other clients natively. So that means there's no additional infrastructure needed. So you can serve a website from a canister smart contract to a browser. Then on that website, your users can quickly create an identity with convenient key management and without downloading anything, using internet identity. And then, thanks to the reverse gas model, no tokens are needed to interact with the canister. And because the canisters run at web speed, users will barely notice any difference to the experience that they are used to from Web 2. And this means that your Dapp lives 100% on-chain, so no cloud involved, and that it also has an amazing user experience. And I want to emphasize again that on the internet computer, Dapps can really run 100% on-chain. Because usually if people say that they build something on a blockchain, what you see on this slide is the reality. So only a tiny fraction of the Dapp actually runs on-chain, and the rest is served off of centralized cloud providers. And this leads to the centralized part of a Web3 service to be hacked, to be regulated, and also to be censored. And one of the reasons we have this situation, apart from the scalability and performance issues that we mentioned earlier, is that the storage costs for other chains are extremely high. So I haven't updated this slide in a while, so I'm not sure if the numbers are still correct for Solana at least. But back then, or on the IC, it still only costs $5 to store a gigabyte of data for a year. And on Ethereum, that's already $110,000, and on Solana, that's already $110,000. But on Ethereum, that's a whopping $80 million. So yeah, pretty expensive. All right, let's come back to subnets for a moment again, because one of the subnets on the Internet Computer is special. And that subnet hosts the so-called network nervous system, or in short, the NNS. And the NNS governs the Internet Computer. So ICP token holders can vote on things like the creation of new subnets, upgrades to a new version of the protocol, the replacement of nodes within a subnet, and many, many other things. So the Internet Computer has an on-chain governance system. And the proposals that are voted on by this governance system can contain actual code changes or upgrades. So when a proposal is executed, the code is also upgraded that has been attached to this proposal. And that's also something pretty unique and a very cool feature, because it really makes the evolution of the IC autonomous. If you think about Snapshot, for example, there's like a project that has a DAO, and maybe they cast votes, or they find consensus through Snapshot. They vote on something, community says 80% yes, we want this, but then there's like nothing binding attached to this vote or to the adoption of that proposal that actually executes what has been voted on within the proposal. So nothing really happens until someone comes along and implements it. But on the IC, that has been flipped around, right? You attach something you want to change to the proposal, and then if that proposal is adopted, the change will actually be implemented, or the code upgrade will actually be executed. So it's very different from what people are used to, I would say. And a concept similar to the NNS is the service nervous system. And the service nervous system, or SNS, allows dApps deployed on the IC to be governed in the same manner that the Internet Computer itself is governed. And that is basically through a DAO. So an SNS is a version of the NNS that's responsible for tokenizing and decentralizing a single dApp. And once a dApp's control has been handed over to an SNS, it can be managed through proposals that are voted on by those that have staked the dApp's native token. And developers can basically now hand over their Web3 service to an SNS. And the community can now acquire governance tokens to take ownership and control through the SNS DAO and shape the dApp's future. Now, let's talk about ICP tokens. So ICP, as you probably already guessed, are the native tokens of the Internet Computer, and they have multiple use cases on the IC. So as already mentioned, they are the currency of the governance system, but in particular, they're used for three things: to facilitate participation in network governance, to reward participation in governance and node machine operation, and they are also used to produce cycles, and cycles fuel the computation on the IC. We'll get to that in a bit. So let's begin with the ICP tokens utility within governance. So as mentioned already, to participate in governance, you need to hold ICP. And participation in governance yields voting rewards. But what people have to do first to earn voting rewards is that they have to lock their ICP in a so-called neuron. And locking means that you cannot transfer the ICP anymore. To do so, you have to specify the amount of tokens to lock and the dissolve delay. You can think of the dissolve delay as a kitchen timer. So if you hit the dissolve button on your neuron, the kitchen timer has to go to 0 before you have control over your ICP again. So if, for example, when you create your neuron, you set the dissolve delay to a year, but for 5 years you don't hit the dissolve button, then after 5 years, if you want to get access to your ICP locked in a neuron and you decide to hit the dissolve button, then it still takes a year because still the kitchen timer has to go to 0 before you actually receive or have control over the ICP again. So that's something to be aware of. Okay, so now that we have a neuron, we can actually vote on proposals and also create proposals. And like I said, people are rewarded in ICP for their participation in governance. And it doesn't matter if a proposal gets adopted or rejected for your voting rewards. The only thing that matters is that you participated, so that you voted. And the amount of ICP that you receive as a reward depends on the number of tokens being locked within the neuron, the dissolve delay of the neuron, and also the neuron age. So as a rule of thumb, the higher the dissolve delay, the higher the amount of tokens being locked, and the older the neuron, the higher the rewards that you receive for your participation in governance. And one pretty cool thing about the NNS is that voting can work semi-automatically. So instead of you having to manually voting on each proposal, which can be extremely time-consuming because there are a lot of proposals, you can set up a follow relation for your neuron. So the NNS has many different topics for different types of proposals. For example, there's a subnet management topic, there is a governance topic, there is a node provider topic, and a couple of other topics. So for each one of the topics, you can set up one or multiple neurons to follow. And usually the neurons that you decide to follow are managed by experts for the respective topic. So for example, for the subnet management topic, most people would probably follow DFINITY's neuron because they think DFINITY has a great expertise within that topic. So they feel like they want to follow DFINITY's lead in that regard. And this approach incentivizes people to vote or configure neuron follows in a manner that aligns with what is most likely to enhance the long-term value of the internet-computer network. And now the final utility, and that is that we can burn ICP to create cycles. But first, we want to understand what cycles actually are. So cycles are the equivalent of gas on the internet computer. So they fuel the computation of canister smart contracts. But as opposed to Ethereum, for example, canisters are actually pre-charged with cycles. And this allows users who don't own any tokens to easily interact with canisters. So they don't need to install a wallet or any other software to be able to interact with a canister. And most of the time, they are probably not even aware that they are currently interacting with a blockchain, which is great because it improves user experience and probably also adoption significantly. So while node provider and governance rewards are inflationary mechanisms, burning ICP for cycles is a deflationary mechanism. So in this economic overview that you see here, you can see that we basically start by node providers that are getting paid in ICP for providing computation to the network. And because those node providers have to pay electricity and maintenance bills in fiat, they are basically selling their ICP on the market to cover those expenses. And on the other side of that market, there are canister owners that buy ICP to then convert the ICP into cycles. It's important to note here that you can't go from cycles to ICP, but only the other way around. So you can only burn ICP for cycles, but you can't burn cycles and then get ICP back. And the cycles that have been bought by canister owners are then sent to canisters and consumed by canisters. And this economic circle or cycle basically starts again. So, might wonder how many cycles do I get if I burn one ICP? So there's actually a fixed rate for the conversion of SDR into cycles. So one SDR is always worth 1 trillion cycles. And you probably don't know what an SDR is, at least I didn't know back then. SDR means special drawing rights, and it's basically a basket of different fiat currency, which helps having a more stable peg, basically. And then we have a cycles minting canister, and that canister gets the rate of ICP per SDR from the exchange rate canister to then calculate the amount of cycles that are being minted for the amount of ICP that you are burning. And this is actually a pretty good example of one of those cross-subnet inter-canister calls that I mentioned earlier, because the cycles minting canister and the exchange rate canister don't live on the same subnet. And the stability afforded by the SDR peg allows for more accurate long-term economic planning and budgeting for the operational costs on the network. So no matter the load of the network, a transaction will basically always cost the same, right? If you think about Ethereum, if the network is under high load, then it might cost, I don't know, $15 to sell your NFT that is maybe worth $10. So that's something that's not happening on the IC, because those transaction costs are basically fixed or pegged to SDR. All right, so now that we have a rough overview of the IC, I want to take the remaining time to brag a little bit with some of the unique features that the IC offers. The first unique feature I want to highlight is HTTP outcalls. And put simply, HTTP outcalls allow smart contracts to directly make HTTP requests to external Web 2.0 servers. And this way, we don't have to rely on oracles to obtain external data, and we can actually interact with the off-chain world. And a good example of a service that uses this feature is the exchange rate canister that I just mentioned earlier, because this canister actually makes calls to multiple data providers, Web 2 data providers, to provide a price oracle for crypto and fiat currency exchange rates. The next feature is chain key ECDSA, which consists of a threshold ECDSA signature scheme, where the private key, like with the other chain key that I mentioned earlier, is shared across the replicas of a threshold ECDSA-enabled subnet. So here, at least 1/3 of the nodes are required to jointly create a signature using their respective key shares. In this way, canisters have control over a unique ECDSA key pair and can request signatures with the corresponding private key to be computed. And from this key pair, for each canister, an unlimited number of keys can be derived. And this technology allows canisters to natively hold Bitcoin or Ethereum and any other chain that supports ECDSA signatures, or tokens of any other chain that supports ECDSA signatures. So that's also pretty huge. Then the Bitcoin integration. So in one sentence, the Bitcoin integration allows canisters on the internet computer to receive, hold, and send Bitcoin, all directly with transactions on the Bitcoin network. And direct in this context means that no trust assumptions are required other than trust in the correct functioning of the Bitcoin network and the internet computer. So in other words, there are no additional parties required, such as bridges or other types of intermediaries, resulting in a much cleaner and also more secure integration. And this means that red Bitcoin from insecure, centralized bridge services, which have been hacked for billions of dollars in the past, are no longer needed in DeFi and Web3. And CKBTC represents a one-to-one backed version of BTC and is built on top of the Bitcoin direct integration. And as the CKBTC ledger is deployed in a canister on the internet computer, it provides fast finality and low transaction costs for your Bitcoin. Then the Ethereum integration. The Ethereum integration allows canisters on the internet computer to receive, hold, and send Ether, all directly with transactions on the Ethereum network. So that probably sounded familiar. And again, just with BTC, there are no trust assumptions required other than trust in the correct functioning of the Ethereum network and the internet computer. And because Ethereum supports smart contracts, as we learned, canisters can now also additionally invoke any smart contract call on Ethereum. And then we have CK-ETH and CK-ERC20 tokens that again represent a one-to-one backed version of the respective asset on Ethereum, and that are also built on top of the Ethereum integration. And they come with the same benefits as CK-BTC, so they offer fast finality and low transaction costs. Then wet keys. Wet keys stands for verifiable encrypted threshold keys, and they enable a number of cryptographic functionalities on the IC. The primary motivation for wet keys is to ease the burden of using security and privacy tools on the internet computer. So, for example, they enable convenient end-to-end encryption for data stored within canisters on the IC, but you can also build deadman switches, secret bit auctions, or time lock encryption with them. So very versatile tool. And the last feature I want to mention is internet identity and easy to use online authentication using fingerprint sensors, Face ID, and any other security hardware on phones and laptops, powered by WebAuthn and advanced cryptography. And here, the cryptographic passkeys are securely stored inside their owners' various phones and laptops, and the private keys remain locked within TPM chips inside the devices, which profoundly improves the security since even the users cannot access those keys directly, right? So in essence, the possession and the control of devices provides the means to authenticate to your internet identity. Another cool feature is that internet identity prevents users from being tracked by using a different cryptographic pseudonym for each service that they interact with. And now that we are nearing the end of the presentation, I want to mention that we've seen some impressive growth since the mainnet launch in May 2021. And if you like numbers, stats, graphs, and such things, definitely check out the IC dashboard to get a sense of what we've achieved already. The dashboard provides data on almost everything you want to know about the network, such as the amount of nodes in the network, the number of independent node providers, how many blocks have you processed since Genesis, how big is the size of the entire state of the IC, how many transactions are currently processed per second, the number of deployed canister smart contracts, and so on and so on. So there's really a lot of data to dig into. We also currently have hundreds of dApps fully deployed on chain, so basically the backend and the front end. And this includes dApps like a Reddit clone, LinkedIn clones, Telegram clone. So check out the projects that are currently running on the IC by visiting this community maintained aggregator called Cycle. It's definitely cool digging around there and seeing what has already been built. And a random subset of dApps on the IC that you could try out. I put them on the slide here. The first one is basically a decentralized TikTok with token incentives. The second one is a fully on-chain AMM. And the last one is a chat application running fully on-chain, where you can, for example, tip users in a chat with crypto and stuff like that. So all of them have unique features that are only possible when building on the internet computer. So that's why I wanted to highlight them here. So maybe to summarize what the internet computer offers, on the IC, you have a reduced platform risk. So if you're building the next big thing, you probably want to make sure that you're not going to be deplatformed like Parler, for example. As a developer, you can focus on building, so you don't need to manage firewalls, load balancing, database configurations, and stuff like that. The internet computer also offers a secure environment for end users, so there are no hack securing. Also, You can use cryptographically secure identities, and you don't have to worry about insecure username and passwords anymore. The Internet Computer also acts as a basis to build trustless multi-chain apps by, for example, directly integrating with Bitcoin and Ethereum, but also by allowing you to integrate with other chains with the threshold ECDSA feature and HTTP outcalls. The Internet Computer is also more cost-effective. It has a higher throughput, lower latency, is more scalable than other layer ones out there. And the Internet Computer offers you a complete technology stack. So systems and services can be created without relying on corporate cloud hosting services or private servers, and thus provide all the benefits of smart contracts in a true end-to-end fashion. And that's very important. All right, so yeah, we've hit the end of the presentation, and I think there are roughly 20 minutes left if you have any questions. I will check the chat first now to see if there were any questions. I see there were questions, okay.
There's quite a few questions in the question tab, if you can see that.
Are there also questions in the chat, or do you think it's enough to just read the questions thing?
Yeah, so let's just say that perhaps if you haven't submitted your question to the questions tab, then please do so now, so then we can just make sure that they're all there.
Okay. Let's see. First question from Arnav. Can we develop on the Internet Computer with Rust? Yes, you can definitely develop on the Internet Computer with Rust. Actually, the DFINITY Foundation itself uses Rust heavily when building canisters on the IC. So Rust is a first-class citizen within the ecosystem. There's a Rust CDK, so a canister development kit that is being maintained by DFINITY. So if you know Rust, then you should definitely go ahead and build a canister with Rust. Possible. Then Matthias asked, do you know if successful dApps in the Internet Computer, say OpenChat, currently publish cost reports concerning their costs of actually running on the Internet Computer Protocol? That is a very good question. Not that I know. They probably do track their cycle burning rate, and it might also be publicly available, but I don't know if they specifically publish any reports concerning their costs. But I would actually recommend you, if you're not part of the forum already, to sign up to the forum and actually ask that question there and tag the respective projects where you would be interested in knowing the cycle consumption. If that's something that they can share, I'm sure that they will share that with you. But if you are interested in the overall rate of cycles that are being burned, that's a metric that's on the dashboard that I mentioned earlier. But of course, that's not as granular as knowing which service burns what. But for OpenChat, for example, I think OpenChat has basically its own subnet. So they have a subnet where only they can deploy canisters, if I'm not mistaken. And if you find that subnet in the dashboard, I think you are able to see the cycles burn rate for this entire subnet. And because all the canisters belong to OpenChat, you could probably kind of like infer the amount of cycles that they are burning. Yeah, that would be my answer. Chakravati asked, any integrations with Ada Cardano? I would like to do something in that space if it's possible. I'm not aware of any plans to integrate with Cardano. So those direct integrations, they require a huge amount of engineering resources. So I think for the Bitcoin integration, it took like 1.5 or 2 years. And I think it's, even though some of the technology can be reused for Ethereum, I think it still takes a year or more than a year to integrate with Ethereum directly as well. But if, I'm not super familiar with Cardano, but if they support threshold ECDSA signature schemes, you can, building on top of HTTP outcalls and threshold ECDSA or chain key ECDSA, you can build, basically applications that integrate with Cardano, even though there's no direct integration. So that's something that's possible. So that's actually how the Ethereum integration works. It's set up in 2 phases. In the first phase, we have this integration where we use threshold ECDSA in each HTTP outcall. And then until we have the second phase ready, we use that. And then in the second phase, we have this direct integration with Ethereum, basically. So I would ask you to research if Cardano supports ECDSA signatures, and if it does, should be possible to integrate with it. Then Matthias asks, can you comment on how are CK-based integrations different from bridging? Yeah, so the difference lies within the fact that the integration, also for CK-BTC, for example, the integration between the Internet Computer Protocol and the Bitcoin network was made in a way that you only need to trust that the Internet Computer functions correctly and that the Bitcoin network functions correctly. So usually when you have traditional bridges, there's always some sort of trust you have to put in the bridge provider, right? So for example, for RepBTC on Ethereum, there is a single entity, I think they are called BitGo, that is responsible for basically receiving BTC and then minting the same amount of RepBTC on Ethereum. And when receiving BTC, a RepBTC, burning the RepBTC and sending the user the respective amount of BTC back. So you have to trust BitGo entirely with that operation. You have to trust them that they don't become rogue, that they don't basically mint RepBTC out of thin air, making them rich without having the BTC. Or on the other hand, that they, if someone sends them BTC to mint RepBTC, that they don't just like transfer the BTC out and spend them on a yacht or something. So yeah, in traditional bridges or bridge tokens, there's always this intermediary that you have to trust. And sometimes they have like some multi-signature setup where it's like not one company, but they're like, I don't know, 7 nodes or something, and 5 out of 7 have to basically like sign off on a minting or burning request. But here again, those have been hacked in the past, where attackers have been able to gather a majority of the key shares, and then they basically could just like create signatures without needing the other guys, right? So not really ideal. And this is a problem that has been solved by directly integrating with Bitcoin and then building CK-BTC on top of that. Okay. Giovanni asked, the blockchain is supposed to be deterministic. That's why they do not query external API, but they need oracles. By querying external API, how can you cope with such a case when the API has been changed so that determinism is lost and you can no longer confirm a past computation? There will be so first of all, regarding Matthias' question, there will be a session on the Bitcoin integration, and that will probably also mention CK-BTC. So if you want to know more about it, I would really recommend you to tune in there. And the same goes for Giovanni's question. There will be a session on HTTP outcalls where we really go into depth on how they work and basically how they enable canisters to make HTTP outcalls to Web2 services. But to keep it short, what happens is that when a canister wants to make an HTTP request, as you know now, a canister runs on a subnet, right? And a subnet basically consists of many independent nodes from independent data centers and independent node providers. So when a canister requests an HTTP, or if a canister wants to make an HTTP request, all the nodes in the subnet, like each single one of the nodes in the subnet, makes this HTTP out call to the respective server. So if you think about this example with calling, for example, CoinGecko's token price API, and the user wanted to know the price of ICP on mainnet launch, then every single node in the subnet where this canister is running on would make the same request to CoinGecko's API. And then they would basically aggregate, or not aggregate, they would basically, so with HTTP outcalls, you can define a transformation function. And what you usually do is that you filter out everything that could potentially be, or could potentially change depending on which node makes the request. So sometimes, for example, if there's Cloudflare in between, Cloudflare will set like some headers that are different for each node that makes the request. So for example, in this transformation function, you would say, okay, I don't care about anything. I get rid of all the headers. The only thing I care about is this JSON that the CoinGecko API returns that contains the price that I'm interested in. And then the nodes in the subnet will basically form consensus on this response that they received. So they will all say, I received this, I received that, I received this. And if they agree that they all received the same thing, then the response from that HTTP request is basically, or has basically gone through consensus, and then it can be returned to the canister. So it was a very high level explanation, but that's basically how it works. If you can't wait until the session, I think it's in 2 weeks, I also gave a session on that in the past. I'm going to share the link in the chat now. So if you want to, it's the Notion document that contains a video recording, and that video recording basically contains what I just said. Okay. With regard to Bitcoin, does this happen on the Lightning Network? No, it does not happen on the Lightning Network. It's a direct integration with the Bitcoin network, no Lightning involved. Then again, but if you call Chakravati asked, but if you call HTTP outcalls, or if you make HTTP outcalls to Web 2, it's not decentralized, right? I guess you leave it to each step to its own secure data from outside. Yes, HTTP outcalls do not solve the problem of decentralization, right? If you build a price oracle and you would only call into CoinGecko's API, then you would be on the mercy of CoinGecko always providing the correct data, right? So if CoinGecko, for example, if the Dapp that you built on top of this price oracle is worth, I don't know, $60 billion, and CoinGecko is able to, I don't know, your Dapp is worth more than CoinGecko, and now CoinGecko thinks like, maybe I short this and I try to crash this. So instead of providing like honest data, I will just provide like completely wrong data in a way that it benefits some malicious thing that I want to do. Of course, that's not a good idea to rely on CoinGecko in that way. But what you can do is that instead of, this is what the exchange rate canister does, instead of like only relying on CoinGecko, you can call CoinGecko, you can call CoinMarketCap, you can call Coinbase, Binance, all of those APIs, and then you basically aggregate the results coming back in a certain way, so that an attacker would basically need to infiltrate a number of data providers, and you are that way a bit more safe. So yeah, the assumption is that it's not really possible for someone to attack all of those data providers at the same time. Yeah, this way you can increase the trust. for your application. How did it happen that, Piotr asks, how did it happen that the SNS token, which was expected to be a governance token, was overtaken by the game developer? That's a very nice question. So as I said, with an SNS, you can decentralize your application. And this SNS token that Piotr is talking about is basically the token from the first SNS that has been created. And this was basically a dry run to check if the process works, if there are any bugs that need to be weeded out. And yeah, so it's basically, it was like a community token. The price per token was extremely small. I think it was 0.0001 ICP per token or something like that. So I think there only existed 10K SNS1. That was the name of the SNS because it was the first SNS. I think there were only 10K tokens or something created or launched when this SNS sale was concluded. So one project on the IC didn't want to launch their own SNS. I'm not sure of the exact reasons, to be honest, but they instead took the route to basically buy up all of the supply of SNS tokens that were on the market. And it turned out that the holders of SNS1 tokens were more than happy to sell their tokens to this game project. So this game project was able to buy up more than 50% of the supply of SNS1 tokens, and therefore they were able to take over the SNS. So it wasn't like a hack or something. So everything worked as intended. The only thing that didn't work was the community evaluating SNS1 tokens enough that they did not sell a majority of all of the tokens in existence to this one person. So that's the only thing that didn't work, that the community basically gave away a majority of the tokens to one person. So this guy bought up the entire network, so to say. Then Peter asked the way how smart contracts are used in EVM kind of networks is very specific and different to traditional model and thinking on Web 2. Is that still possible to use containers, I guess canisters, in a way they behave just like smart contracts on EVM-based blockchains, so you can use them, for example, for tokenization? I'm not sure I entirely understand the question, but what I can say is that you can definitely use canisters to tokenize a project. So you can just do the exact same thing of setting up an ERC20 token contract on the internet computer. So that's possible. It's just like canisters are like basically they offer like a superset of the functionality that Ethereum smart contracts offers, right? So they are like an evolution. You can do everything you can do on Ethereum smart contracts and even more. So I guess the answer is yes, but maybe you meant something else. Then there was a question for Encode Club. I'm going to skip some of the questions where I know that I won't be able to answer them. And I would encourage you to ask them in the forum, actually. And this is the place where the experts on every topic are. Maybe Giovanni, Giovanni asked, who owns the data centers? So the data centers are owned by, it's maybe the wrong term, but just by random companies, right? So there are data centers that do not belong to Google, Amazon, or Microsoft. So those are just people that have data centers, so they have rack space available, and they are independent to those cloud providers. So yeah, they are basically just owned by random companies. It's a business model to have a data center. It's just like a normal company, like people that rent out warehouses or storage spaces or something. It's a similar concept, I would say. So yeah, a lot of different people or entities own those data centers. And if you go to dashboard.internetcomputer.org and then /centers, maybe I will quickly share my screen. It's probably easier than talking about it. So here, for example, this is the URL I just mentioned. You can see the data centers that are currently registered with the Internet Computer. So as you can see, there are different owners for them. For example, this one is owned by Data Center United and located in Europe and Belgium. And let's go to page 6 and pick one randomly. This one is owned by a company called Flexential, and it's in North America, in the United States, in Oregon. This one is owned by a company called CyrusOne. Yeah, so I would say those data centers do not exist solely to host ICP nodes. They are just data centers, and they happen to also host ICP nodes, but they host other nodes or other server infrastructure for other companies as well. Maybe medium-sized enterprises or something like that want to run their own server hardware instead of relying on AWS, Google Cloud, and so on. Yeah, I hope that answers the question. Okay, let's see. Can I run another blockchain like Ethereum node in the Internet Computer? I'm not entirely sure what that means, so I have to skip that one. But I would tend towards no. Yeah. Let me read another one.
I think for now, if possible, is it possible for you to maybe leave a point where they can ask these questions? Because I think we have to finish the session pretty soon and wrap up. I don't know if you have a preferred way you want people to contact you or ask questions, or where you think that they can get answers to these questions.
Ideally, I would ask people to post those questions in a developer forum. I think that's probably the best place for most of the questions. And you can tag me directly there. Then I will try and answer them or find someone who's capable of answering. And my handle is basically the same as my Twitter handle, so I put it in the chat. It's Crypto Schindler. And the forum link is forum.definity.org. And maybe again the link to the slides, because the forum link and other links are in there as well. So also put it in the chat. Yeah, I think this would be the best way of proceeding.
Amazing, thank you. So yeah, thank you so much for joining and taking the time to answer at least some of the questions and deliver a really good introduction to the Internet Computer. So yeah, thank you everyone as well for joining. Hopefully I'll see you guys as well on Thursday, when we are doing another session about canisters. So make sure to join that same time. And have a nice rest of your day, everyone. Bye.
Bye, everyone.